The San Andreas Fault just did something scientists have never confirmed seeing before on a fault like this, and the discovery came not from a sudden earthquake, but from 8 years of quiet data that nobody had actually finished looking at until artificial intelligence went through it. So let's get straight into what was actually found, how it was found, and why researchers are calling it a genuinely new piece of the puzzle, rather than just another headline about California shaking. Here's the core of it. A research team led by Dr. Zara Zali at the GFZ Helmholtz Center for Geosciences, working with EarthScope and Stanford University, published a study in Nature Communications on June 9, 2026, describing something that had been sitting inside the monitoring network at Parkfield, California for years, without being fully cataloged. Dozens of previously undetected slow slip events, quiet, non-shaking fault movements that had gone unnoticed inside enormous volumes of continuous strain data. Using an unsupervised deep learning method, the team identified 92 short-duration slow slip events along the Parkfield segment of San Andreas Fault, including 21 that had never appeared in any prior manually compiled catalog. And when they compared the timing of these events against a separate category of weak seismic signals called low-frequency earthquakes, they found something that had never been documented this clearly on a strike-slip fault before. A consistent pattern where seismic activity increased specifically after these quiet slip events occurred. Let's slow down and unpack every piece of that, because each part matters for understanding why this is being taken seriously, rather than treated as just another data point. First, what is a slow slip event, and why is it different from an earthquake? A normal earthquake releases built-up stress in a fault suddenly, typically over a matter of seconds, which is what produces the shaking we feel, and what a seismograph records as a sharp spike. A slow slip event rarely eases a comparable amount of ground displacement, but instead of happening in seconds, it happens gradually, over minutes, hours, or in some documented cases at other fault systems, over days or weeks. Because the motion is so gradual, it generates little to no shaking that a normal seismometer would register as an earthquake. It shows up instead as a slow drift in extreme, ALE-sensitive instruments buried underground, specifically designed to catch deformation too subtle for standard equipment. Researchers sometimes refer to these informally as silent earthquakes, though that's a loose shorthand rather than a technical term since they aren't classified as earthquakes at all. Slow slip events aren't new to seismology in general. They've been documented for roughly 2 decades along subduction zones, places where one tectonic plate dives underneath another, like the Cascadia Zone off the coast of Washington and Oregon, and the Nankai Trough in Japan. What made the Parkfield findings different is where they were found. The San Andreas is a strike-slip fault, meaning the Pacific Plate and the North American Plate slide horizontally past each other rather than one plate diving beneath the other, documenting a large, clean, well-instrumented catalog of these short-duration slow-slip events specifically on a strike-slip fault, and demonstrating a clear, repeatable link to increased low-frequency earthquake activity afterward is the part researchers are describing as new. Now here's how they actually found it, because the method itself is a meaningful part of the story. The research team analyzed roughly 8 years of continuous borehole strain meter observations at Parkfield, one of the most heavily instrumented stretches of fault on the planet. Borehole strain meters are extraordinarily sensitive instruments installed hundreds of meters underground, sensitive enough to detect deformation caused by ocean tides pulling on the crust from hundreds of miles away. That level of sensitivity is exactly why they can catch a slow slip signal that would be completely invisible to a standard seismometer, but it also means the data streams they produce are enormous and full of environmental and instrumental noise that has to be filtered out before any genuine tectonic signal can be identified. For years, that filtering was done largely by manual inspection, researchers examining data by eye, which naturally limits how thoroughly any data set this large can actually be searched. What the Zali team did differently was apply an unsupervised deep learning workflow, essentially training a neural network to recognize recurring deformation patterns in the data on it, as its own, without being told in advance exactly what a slow slip signature should look like. The algorithm learned to separate likely tectonic events from background noise using a technique involving compact latent representations of the strain data, then clustered similar signals together. When they tested this method against an existing manually compiled catalog of known slow slip events, the algorithm successfully recovered about 90% of those previously known events, which is itself a strong validation that the method works. But it also flagged 21 additional events that had never appeared in any manual catalog before, events that had simply been missed by human review across years of continuous monitoring. That's an important distinction to sit with for a second. This wasn't a case of new instruments picking up something that hadn't existed before. The data had already been collected. These slow slip events had already happened sometime within that 8-year observation window. What changed is that a new analytical method was finally powerful enough to find signals that had been sitting inside existing data the whole time, waiting to be noticed. To make sure those 21 newly identified events weren't some kind of algorithmic artifact or false positive, the researchers cross-checked them against a completely separate type of instrument, creep meters, which measure fault displacement using a different physical mechanism than strain meters. 14.0. If those 21 new events were independently confirmed by nearby creep meter readings, which is a meaningful form of validation because it means two different instruments, measuring ground deformation in two different ways, were picking up the same underlying physical event. That kind of cross-instrument agreement is exactly what separates a credible geophysical finding from noise or coincidence. So what do these events actually look like physically? The team's analysis found that the transient deformation occurred at shallow depths, generally less than about 4 kilometers, or roughly 2.4 miles down, and that the direction of slip was consistent with right lateral motion, meaning the specific sideways sliding pattern that characterizes the San Andreas Fault as a whole. In terms of duration, these newly cataloged short events typically lasted somewhere between 25 and 100 minutes, filling in what researchers describe as a previously observed gap between ordinary earthquakes, which release energy in seconds, and the much longer slow slip episodes at other fault systems that can stretch across days or weeks. This Parkfield catalog sits in the middle of that spectrum, a scale of fault behavior that had been difficult to observe clearly before because it required exactly this combination of high sensitivity data and a method capable of pulling weak signals out of years of noise. Now for the part that's driving most of the follow-up scientific interest, the connection to low-frequency earthquakes. Low-frequency earthquakes, often abbreviated LFEs, are a distinct class of weak seismic signals associated with fault slip processes, different in character from the Schutzschar, ARP, broadband signal of an ordinary earthquake. When the research team overlaid their new slow slip catalog against records of LFE activity in the same area, a clear pattern emerged. LFE activity consistently increased following the occurrence of a slow slip event. The relationship was strongest specifically for low-frequency earthquakes occurring within about 10 kilometers, or roughly 6.2 miles, of the reference strain meter, and at depths shallower than about 20 kilometers, or 12.4 miles. In plain terms, after one of these quiet slip events happened, the surrounding fault segment tended to become measurably more seismically active in this specific low-frequency way, in a consistent, repeatable pattern rather than a one-off coincidence. That finding matters because it suggests these quiet, non-damaging slip events aren't happening in isolation, disconnected from the rest of the fault's behavior. Instead, they appear to be actively modifying stress conditions within the fault system in ways that influence what happens next, seismically, in that area. As one of the study's co-authors, Professor Patricia Martinez-Garzon of the GFZID Helmholtz Center put it, these slow fault movements appear to be linked to changes in seismic activity, suggesting slow slip may play a meaningful role in how stress evolves along active faults over time. There's a second finding in the study worth understanding on its own because it touches on a long-standing assumption in how scientists model these events mathematically. For years, many studies describing slow slip events used what's called a linear moment-duration relationship, essentially a mathematical rule connecting how much total movement and even t produces to how long it takes to unfold. The Parkfield observations instead point toward an approximately cubic moment duration scaling law for these short duration events, a relationship that places them much closer to the scaling behavior seen in ordinary fast earthquakes than the linear relationship that had been assumed for slow slip more broadly. The researchers are careful to note that more observations will be needed to fully pin down the geometry involved, but this finding adds evidence that at least some forms of quiet, aseismic fault slip may follow physical scaling rules closer to those of ordinary earthquakes than previously assumed, which is a genuinely new wrinkle in how scientists think about the physics connecting these different categories of fault movement. Now, let's put this in the context of what Parkfield actually is and why it's been the site of this kind of research for decades in the first place. Parkfield sits along the central section of the San Andreas Fault in California, and it's often described as one of the most heavily instrumented stretches of fault anywhere on Earth. That's not an accident. This particular segment is known among seismologists as a creeping section, meaning it regularly and gradually releases accumulated strain rather than storing it up for a single massive rupture, the way the locked segments to its north and south tend to. Because of that behavior, and because it has a long history of producing moderate, repeated earthquakes in a relatively predictable pattern, Parkfield has functioned for decades as a kind of natural laboratory, a place where scientists can study the fundamental mechanics of how faults accumulate and release stress at a manageable scale. with the hope that lessons learned here can inform understanding of the more dangerous, locked segments elsewhere along the fault. It's worth understanding a bit more about why Cascadia and Nankai keep coming up as reference points in this kind of research, because the comparison isn't incidental. At subduction zones like Cascadia, slow slip has been studied intensively, at least since the early 2000s, and researchers there identified a phenomenon called episodic tremor and slip, where slow ground movement is accompanied by a faint, continuous seismic hum, distinct from the sharp signal of a normal earthquake. That combination, slow slip paired with tremor, became a well-established signature at subduction zones over roughly 2 decades of research. What had been much harder to establish is whether that same combination, or something structurally similar to it, also shows up on strike slip faults like the San Andreas, where the underlying plate geometry is completely different, sideways sliding rather than one plate diving beneath another. Parkfield has actually been a site of tremor research for years already. Low-frequency earthquakes and tremor signals in the deep roots of the fault near Parkfield had been documented before this study, including transient slow slip events detected at around 16 kilometers depth using GPS networks in earlier research. What the new AI-driven strain meter catalog adds is a much more complete picture of the shallower, shorter duration end of that spectrum, the part that had been the hardest to separate from noise using older manual methods. That said, it's worth being precise about what's actually new here versus what builds on existing research. Slow slip and tremor near Parkfield were not undiscovered concepts before this paper. Scientists have been documenting various forms of aseismic slip on this exact fault segment for roughly 2 decades, using PS, creep meters, and strain meters in different combinations. What this specific study adds is the scale and completeness of the catalog, the use of an unsupervised AI method capable of finding events that manual review had missed, and, most significantly, the clear statistical link between the newly completed slow slip records and subsequent low-frequency earthquake activity, demonstrated with a level of completeness that hadn't been achieved on this fault before. It's an advance built on 2 decades of prior groundwork, not a discovery arriving out of nowhere. That broader context is worth having, because the San Andreas as a whole is not a single uniform structure. It runs roughly 750 miles through California, from the Salton Sea in the south, up through the Bay Area, and out toward Cape Mendocino in the north, marking the boundary between the Pacific Plate and the North Am. Eric and Plate as they grind past each other. Different segments along that length behave very differently. The fault produced the 1906 San Francisco earthquake, an estimated magnitude 7.9 event that ruptured close to 300 miles of the northern segment, and, combined with the fires that followed, killed an estimated 3,000 PE. Opal. Further south, the fault last ruptured in a major way back in 1857 in the Fort Tejon earthquake, also estimated near magnitude 7.9, which tore through nearly 200 miles of the southern section near what is now Los Angeles County. That southern segment has now gone more than 165 years without releasing in a similarly large event, a stretch of quiet that seismologists generally regard not as reassuring, but as an indication of significant accumulated strain still waiting to be released eventually. USGS hazard models place the probability of a magnitude 6.7 or larger earthquake occurring somewhere along the broader California fault system at roughly 75% over the next 30 years, with the San Andreas carrying some of the highest individual segment probabilities of any fault in the state. It's important to be precise here about what this new Parkfield research does and does not tell us in relation to that broader hazard picture. This study is about historical data, roughly 8 years of it, analyzed retrospectively using a new method. It is not a live unfolding event, and the researchers themselves are explicit that these newly detected slow slip events are not earthquakes, and should not be interpreted as evidence that a damaging earthquake is imminent anywhere along the fault. What the study does provide is a clearer, more complete picture of a specific, previously underobserved category of fault behavior, and evidence that this quiet behavior is more tightly connected to subsequent seismic activity than earlier models had captured. That's valuable for refining how scientists understand stress transfer and fault mechanics generally. It's a different thing entirely from a prediction about timing, location, or likelihood of any specific future rupture, and the researchers have been careful not to blur that line. It's also worth understanding why this method itself matters beyond this one fault segment. As geophysical monitoring networks continue to expand worldwide, adding more instruments and collecting ever larger volumes of continuous data, researchers increasingly run into a practical problem. There's simply too much data for manual, by-eye analysis to thoroughly examine. The Parkfield study is a demonstration of how a properly validated AI method can sift through years of continuous observations and surface subtle deformation patterns that conventional workflows, however careful, would likely have missed. That has implications well beyond the San Andreas. Any fault system with a comparably dense LA, long-running instrument network, whether in Japan, New Zealand, or elsewhere, is a candidate for the same kind of retrospective reanalysis, potentially revealing similarly hidden events sitting inside data that's already been collected, and in some sense, already sitting on a hard drive, somewhere waiting to be properly examined. Let's also be clear about what this finding does not mean, because it's easy for a story like this to get inflated into something scarier than what the actual research supports. It does not mean a major earthquake is now more likely within any specific time frame than it was before this study was published. Slow slip activity has occurred at Parkfield many times over the decades without triggering a large rupture on the adjacent locked segments to the north and south. It does not mean the scientific community was caught off guard by fault behavior it didn't understand. Parkfield's dense instrumentation was built decades ago specifically so that subtle behavior like this could eventually be captured. URED and studied with precision, which is exactly what happened here, just later, and with better tools than were available when the data was first collected. And it does not represent some kind of unprecedented physical event happening to the fault right now. It represents an improved scientific view of behavior that had already occurred, made visible through a better analytical method applied to existing records. What it does mean, in plain terms, is that scientists now have the most complete and best validated catalog yet of a specific category of quiet fault movement on a major strike-slip fault, along with the clearest evidence yet that this quiet movement is systematically connected to subsequent low-frequency seismic activity nearby. That's a real, meaningful added ion to the scientific understanding of how the San Andreas, and potentially strike-slip faults more generally, actually behave between the large, damaging earthquakes that make headlines. Filling in that middle ground, the quiet, non-shaking part of the fault-slip spectrum, is exactly the kind of incremental but genuine scientific progress that eventually feeds into better hazard models, even though it doesn't come with a specific prediction attached to it. Now, since this research is specifically about the San Andreas, it's worth briefly grounding where Parkfield sits relative to the parts of the fault most people are actually concerned about day to day. To the south of Parkfield, the fault continues through what's called the Colomé segment, and then the Carrizo Plain where you can still see T, the actual offset in the landscape left behind by the 1857 rupture, visible even from satellite imagery today. Further south still, the fault runs near San Bernardino before connecting into a complex set of fault junctions near the Salton Sea. To the north of Parkfield, the fault continues up through the Santa Cruz Mountains, the segment. T responsible for the 1989 Loma Prieta earthquake, a magnitude 6.9 event that killed 63 people and caused significant damage in the Bay Area, including to a section of the Bay Bridge. From there, the fault runs up through the Bay Area itself before reaching its northern terminus near Cape Mendocino. Stress transfer between end fault segments, meaning the idea that movement in one section can redistribute pressure onto neighboring sections, is a real, well-documented mechanism in general seismology. But it doesn't behave uniformly or predictably across long distances, and this specific study doesn't claim to demonstrate a new stress transfer event actively propagating toward those adjacent segments. It's a retrospective catalog and analysis, not a live monitoring alert. It's worth touching on what happens next with this research. Since a single published paper is rarely the end of the story in an active field like this, findings like these typically move through additional scrutiny after publication, other research groups attempting to replicate the method on different segments of the fault, or applying similar deep learning approaches to other heavily instrumented fault systems to see whether the same relationship between slow slip and low frequency earthquake activity holds up elsewhere. That's a healthy, normal part of how a genuinely new fin gets tested and either strengthened or revised over time. The Zolli team's own paper is explicit that additional observations will help better constrain the geometry of these events, which is scientific language for saying this is a strong first result rather than a final settled picture. The next back. CT follow-up studies, potentially applying the same or similar AI methods to the locked segments north and south of Parkfield, or to entirely different fault systems elsewhere, as researchers test how generalizable this approach and this specific finding actually turn out to be. It's also worth being honest about the limits of what a single retrospective study like this can tell us, even a well-validated one. 8 years of data from one segment of one fault is a meaningful sample, but it's not the same as a real-time monitoring capability that could flag a similar pattern developing live and tell scientists something is actively unfolding right now. The method demonstrated here is fundamentally a tool for analyzing data that's already been collected, searching more thoroughly through the past rather than predicting the future. Whether or how quickly this kind of deep learning approach gets adapted into a live real-time monitoring pipeline, neither could flag a slow slip signature as it happens, rather than years later, is a separate engineering and validation question that the current paper doesn't answer, and it's worth not assuming that leap has already been made just because the underlying detection method has been shown to work well on historical records. It's worth closing on the practical takeaway, since that's ultimately what most people watching a story like this actually want to know. If you live anywhere near an active fault system, whether that's California, the Pacific Northwest, or anywhere else with meaningful seismic risk, the STA. Ending. Sensible advice hasn't changed because of this study, and it doesn't require panic. Know your evacuation routes, keep a basic emergency kit with water, food, and a flashlight, and make sure heavy furniture in your home is properly secured. California's Shake Alert early warning system, now covering the entire St. Coast, can provide anywhere from a few seconds to roughly a minute of warning before shaking arrives at a given location. Enough time to automatically slow trains, open fire station doors, and give people a chance to drop, cover, and hold on before the worst of the shaking begins. None of that infrastructure, and not Hing in this new research, changes the fundamental fact that earthquakes cannot currently be predicted with a specific date or time attached. What this study does is give scientists a genuinely new, better resolved piece of the picture of how the San Andreas actually behaves in the quiet stretches between the earthquakes everyone already knows about. And that's exactly the kind of finding worth understanding accurately without needing to dress it up as something it isn't.